So the talks this morning were extremely interesting because they show you stories of microservices in production. And one of the questions that arises when you run microservices in production is, how do you manage the complexity of a system that has, as we've seen, maybe 200, 300 moving parts? I think this is kind of analogous to the question, how do you tell if a human being, how do you tell if a person is healthy? You don't do that by measuring the flow rates of ion channels in cells. You use emergent properties. You measure things like pulse or blood pressure. And these emergent properties give you a generalized measure of the health of the system. And this idea can be transplanted to microservice-based systems. And it's a different approach to measuring the health of these systems than one would use traditionally in IT, where you're looking at response times of endpoints and things like that. And you would have seen actually in the Halo talk in particular, a really good example of a dashboard which is looking at generalized health. You know, don't let the streams cross. So these ideas around how you measure and how you handle the chaos that are microservice systems kind of come from our own experiences building these types of systems over the last 3 or 4 years. So my company Nearform that I founded with Kian, who introduced the conference this morning, we started off building Node.js systems and very quickly realized that microservices were a really good way to build Node.js systems. And our experiences are slightly different from the ones you would have heard this morning, in the sense that the ones this morning are focused on building very large systems, and the people who've built them have had time within one company to evolve the systems and put them together with fairly constant teams. Our experience is quite different in that we build systems for our clients, which means that we build systems sometimes for very large companies, sometimes for startups, systems that have to scale, systems that are maybe internal apps, all sizes and scales and all different skill levels in the teams. And this talk is really, in a sense, part of a report on our experiences. So I'm not being prescriptive as such in this talk when I talk about some of the techniques that we've used. This is more a report on the empirical learnings that we've seen over the last couple of years. But I think it is relevant to using microservices as a tool for rapid innovation, as a way to build services very quickly, but then also answering the question, how do you mitigate the risk of essentially allowing developers to build things chaotically without all of the traditional controls that you would have in place? One key question, one key point that is important is this idea of what microservices are. And if you look at a lot of the literature, a lot of the blog posts, a lot of the books out there, it's easy to form the impression that microservices are essentially very small web servers. And even if you looked at the Netflix diagram where it was this tree graph, you see that is the predominant design. But you'll hear from Fred George later this afternoon that there are other types of architectures, especially very strongly asynchronous types of architectures. So I think it's important to understand microservices in a very general way, because it is a powerful and general pattern where it's about messages being communicated between independent processes. And actually this allows us to flip the understanding on its head. In one sense, you can view it either as a system of very small services, or you can view it as a system of messages which are flowing between different services. And a message-oriented view of the system is a very, very useful thing, very, very useful way to view the system, because it gives you a homogeneous understanding of what's going on. Message flows between different services are the same sorts of thing, as opposed to individual services which may have different performance characteristics in terms of memory or CPU or caching or whatever. So this behavior of messages is something that, and again, this comes from our empirical observations and our experience, is something that seems like a fundamental characteristic of microservice systems. It seems like it's something that is the part that you have to pay attention to. And as we try to control our microservice systems, as we try to control them in production and try to answer questions about why, when I deployed this service, did everything suddenly break, instead of looking at the behavior of individual services, instead of taking the traditional view where you take a service, you test it, and then you deploy it, and everything should be okay, that wasn't working, you look at what's happening to the message flows. Because it is the flows of messages between services that is something that gives you a fundamental understanding of the system. Message flow rate is a very simple measure that you can apply to any of the messages. And it's independent of the services. So if I have a user logging into a system and I'm generating user login messages that announce that this user is logged in, if I have 10 users per minute, I've got 10 messages per minute, independent of whether I have 5 or 10 or 20 services servicing those messages. So I'm independent of the number of services, I'm independent of the topology of the network. I'm measuring much more closely to the behavior of the system and the things that I care about. And again, this is a homogeneous measure. It applies across the board to all the different types of messages that you have. And it is something that is very easy to measure, something that gives you understanding without having to develop complex tooling. So let's look at a practical example. Let's say I deploy a new version of my user login microservice. And what I'm doing is I'm counting the number of user login messages per minute, let's say. And you can see on the chart, it starts off at around 80 per minute. And maybe this is after lunchtime, and you can see the trend is downwards. And then I deploy a new version of my user login microservice, and suddenly something happens to the chart. The number of login messages slowly decays away. And you saw a chart very similar to this, actually, in one of the talks this morning, where you deploy a version, something goes horribly wrong, and the count of messages goes down. This tells you that the new version is broken. And it gives you the ability to say, okay, now I need to perhaps roll back because this new version of the service has broken things. And this applies irrespective of whether you've fully tested your microservice or not. So this happens in practice with microservices that pass all the tests because the system itself is chaotic, because there are so many different interacting parts. It's impossible to tell just from the traditional measures whether the microservice, the new version of the microservice, is going to work. You have to test. You have to measure against the production system. These things tell you if your system is healthy. And you can see when you deploy a service if the system has remained healthy. There is no way to do that with these complex interactions using our traditional measures. The thing to do then is to say, okay, well, how can we use this idea to actually take back some control and to actually obtain the benefits of microservices, which is this rapid innovation, the ability to deploy things on a continuous delivery pipeline really, really quickly. It's difficult to know what flow rates to measure, which messages count, which ones are important. You have to say, okay, well, maybe there's 200 services, maybe there's 500 different types of messages. Am I going to have 500 different measures? Which ones are important? Which ones actually count? What this feeds into is another aspect of microservice architectures, another part of the discovery process that we're going through, which is to ask the question, what are the patterns of communication between microservices? And we can use these patterns to start understanding which flow rates are important. And these are just a couple of the patterns that we've discovered. I'm sure that ultimately there will be a pattern catalog, and we'll have a much better description of these. But these are the ones that we've seen most commonly in practice. The actor pattern is extremely common. This is where I might have a number of different user login services, and there's a load balancer in front of them, and in a round-robin fashion, each one after the other, processes the next message. This is extremely common, especially when you're trying to handle load. The subscriber pattern is another one that we often see. So if you've looked at any of the videos of talks that Fred George has given online, you'll see this is one that he commonly talks about where you're trying to generate special offers for a user coming in. And you have a whole bunch of different services that generate special offers, and then you rank them. This is a very, very common system. In fact, if you prefer availability over consistency, you can use this pattern in ways that you wouldn't normally expect. So, for example, if you're calculating sales tax, you might actually have a number of different sales tax services, some of them which know about special rules, some of them which know about individual countries, and some of them which don't. And then they all generate the sales tax number for your particular e-commerce shopping cart, and you rank the results in some way. So this pattern is very, very common because it gives you very high reliability. This pattern is also one that occurs a lot, especially when you need to process things in series. So this might happen with an e-commerce checkout system where you need to process the checkout, you then need to send an invoice, and then you need to send an email or something like that. So one service after another, messages pass off between the different services. And finally, if you generalize that, you have a chain where an individual message causes a flowering of other messages into different systems. These patterns are ones that we see again and again. And you can see this is kind of a generalization of the idea of messages between services rather than thinking in terms of just individual point-to-point communications. So if we step up a level and we ask, why are we building microservice systems? I think part of the reason is it reduces the risk of moving fast. Continuous delivery, the ability to write something in the morning and deploy it in the afternoon, is something that we need to deliver as software engineers. The problem with that is that it's a risky activity. And you can build delivery pipelines. You know, Jenkins builds your system, and it runs your tests, and then it deploys. And we have built systems like that. The problem is when microservice systems get very big, they have emergent properties, they have chaotic behaviors, your unit tests may not have discovered the fact that an individual service is generating poison messages that are then causing a cycle of crashes in other microservices. In order to deploy individual microservices safely, you need to have a way of managing the risk. And the important thing is to think about risk in the right way. So part of what we're trying to do when we have unit tests and when we have software development processes is we're trying to reduce risk. But you have to ask the question, all of these traditional best practices, how much are they reducing the risk? And I don't ask that as I ask that in a very literal way. How much? What is the measure of risk reduction? Is there a number that you can put on it? And what you find with a lot of people who advocate, 100% unit test coverage or Scrum or something like that is that they are making these kind of crazy claims that you can eliminate risk altogether. If only you followed the process properly, then the system would have been delivered on time. Right? How many times do we hear that? It didn't fail because Scrum doesn't work. It failed because you didn't follow Scrum 100%. The problem is these are not good measures. We need measures that can give us actual numbers that say the risk of deployment is such and such. The probability of failure is such and such. We have to find good measures. And all of the things that we are using, these are all necessary things like unit tests and code reviews. We shouldn't throw them away, but we should be very careful about how we use them in our thinking. Many times, systems have fully passing unit tests, and yet when they're deployed to production, they fail. For other reasons, right? They weren't performance tested properly, or the live data interacts in some different way. Simply having 100% unit test coverage doesn't guarantee that something is going to work in production. So we have to find different ways of controlling the risk and different ways of measuring the risk. And the problem is microservices have made things worse. So all these things apply to monolithic systems. Well, these questions about give me an exact measure of risk applies to a monolithic system that you're deploying once a quarter. But now, when we're using microservices and we're deploying lots of different microservices 50 times a day, as you've seen this morning, we now have all these emergent issues as well. So our systems are actually more unstable. So microservices actually made things worse. So this is part of the way that we've tried to attack this problem, because obviously we have to deploy systems that really work. And we've attacked it from two different sides. One is this measurement of the production system that I spoke about earlier. And another is the application of formal methods at the front end of the process. So the measurement of the production system tells you when you've deployed something, is it going to break? And you can look at the charts and try and use those to see, have I done something wrong? The formal methods approach goes to the other end and says, can I specify the system in a way where I can have some knowledge of how much risk I'm taking on? So has anybody here actually, put up your hand if you've actually used formal methods or been paid to use formal methods? Very good. One person. Formal methods are proving mathematically that a system is correct. And they're extremely expensive, and they're not exactly that practical. I think the Paris metro system was specified in the Z language, for example. But it's not practical for most enterprise development, especially at the pace and the speed that we need to work at. However, there are approaches which do work. And one of the ones is to use something called TLA+. So you might be thinking, that learning Go or Swift or something like that might be an interesting exercise as the next language that you learn. I would advise you to take a look at this language. This language is a formal specification language. But the way it works is like a chess computer. It explores the state space of the system down to a certain level. It doesn't prove that it's correct. It comes up with a probabilistic measure of correctness. And this system was invented by a guy called Leslie Lamport, who is the guy behind LaTeX and the Paxos algorithm and vector clocks and stuff like that. And he invented or came up with TLA as a way to formally specify distributed systems. So this is actually a perfect language for formally specifying what we expect microservice systems to do. And it's surprisingly easy to learn. So if you look at this specification here, it's a specification for a 12-hour clock. And all it's saying is that the hour variable must be between 1 and 12. It can't be 0, it can't be 13. That's all it's saying. And at the bottom, the theorem line just says it should always be true that the hour variable is between 1 and 12. And you can use systems like this to specify how each individual microservice should behave in terms of the messages that come into it and the messages that come out. It's actually not that difficult to learn. And it's something that I would recommend if you want to think of yourself as a software engineer. These are our differential equations. These are the types of things that we should be using to really do engineering. However, there are some very useful ideas that you can take away from TLA plus and formal methods that you can use straight away without having to learn anything new, which is the idea of invariance. The specification that I showed you had an invariant. The hour variable could not be outside the numbers from 1 to 12. And if that invariant was broken, then the system is broken. So you can ask the question, what are the invariants in my microservice system? If I can identify those, I can measure them, and then I can know that my microservice system is OK. And I don't need to learn formal methods to do that. So here's an example. Let's say I have an e-commerce shopping cart. And every time I add an item to the shopping cart, I'm generating an add item message. And I also have a sales tax service that's calculating sales tax for me. And it needs to get it returns a sales tax message to say, here's the sales tax on this particular item. And every time I add an item to the cart, I should have an add item message, and I should have a sales tax message. And the ratio of those messages should always be 1-to-1. So in this chart, the top two lines, which are kind of mixed together, show me the number of add item messages per minute and the number of sales tax messages per minute. But the bottom line shows me the ratio, and that's the useful measure. That's like an engineering measure. It's like a tolerance in a factory, because that should always be 1, pretty much, right? Between 0.98 maybe and 102. That's something that you can measure in production to make sure that your system is okay. Because if you're trying to measure, for example, against the number of logins per minute, that might be 80 at lunchtime, but 1 at midnight. It's a difficult thing to measure, but the ratio of message flows is constant. It's always the same across your system. Finding these things is actually easy if we go back to the message patterns, because the patterns give us simple invariants to test against. We know a priori what our patterns are because we designed them ourselves. We've said this is an actor system, this is a subscriber system. We can find invariants directly from those designs. For example, in the actor pattern, we know that if there's n actors, then each of them should receive 1/n messages. That's something that you can measure and put on a dashboard. When you deploy a new version of the actor, if the measure doesn't stay 1/n, you know you've done something wrong and you can roll back straight away. We don't need to do deep mathematical analysis of the system. This is pretty much just given to us. The same with subscriber, right? N subscribers means there has to be n messages. These are really, really simple things to measure. You're just counting the messages per minute and seeing, do they make sense in terms of the patterns that you're using in your system? The same with chain, for example. We know there's a specific number of steps. With the tree system, you might measure the number of leaf messages that arrive at the endpoints of the chain. There's all sorts of different variants. But if you take these common microservice patterns, you can ask what the invariants are. The invariants are pretty easy. Now you have some really good measures for the health of your system. That means that when you have 200 microservices and you deploy a new one, you can see, do any of these measures change? And instead of measuring 300 flow rates, you have measures which directly correlate against the health of the system because they directly measure the intended behavior of the system. This is kind of inspired, so we came up with this approach. We were looking for a way to do this. And we came across this approach because it's something that Amazon has been using for a while. So data destruction bugs in things like S3 and DynamoDB are really bad. But they're distributed systems. And Amazon was looking for a way to verify that these systems did not have data destruction bugs. And this is where they started applying things like TLA+. And in fact, if you, and there's a link there, and we'll share the slides afterwards, but if you read that article, Amazon formally simulated S3 and DynamoDB, and I think in the case of DynamoDB, they found a data destruction bug 15 or 16 steps into the execution of a particular path out of all the possible trillions of paths. Now, Amazon obviously had enough compute power to run the simulation for a couple of weeks, but nonetheless, Amazon has a probabilistic measure of risk in the structure of their distributed system using this technique. Now, you don't need to go the whole hog the way Amazon has done and write a formal system. You can use the basic idea, which is, what are the invariants? Are they being kept? And may give you a very good measure, because if your invariants are going out of bounds, you know that there's something wrong in your system. And the degree to which they're going out of bounds gives you a measure. It also means that instead of trying to fight the tide of thinking of every possible error, you're actually thinking about what the system should do. And I really like this quote from a guy called Chris Newcomb in AWS, who kind of pioneered this technique. Ask not what can go wrong, ask what must go right. And invariants are what must go right. And if you're specifying what must go right, you're expending mental energy in the right place. So, for example, you deploy a new version of a microservice. Should you roll back? Well, if we apply the idea of invariants, perhaps the user login generates 2 additional messages. Maybe one is an audit trail, and maybe one it loads the user profile. So the ratio should be 2. Now we deploy a new user profile microservice, and the ratio goes down to 1. And we know that we've broken something. This is a safe and solid measure. It doesn't matter about the rate of traffic in the system. It doesn't matter if you're running multiple versions of the user profile. You know that if you've changed something, it's broken. This works if you maintain discipline about how you deploy microservices. You should never end up in a situation where you have coupling, where you're deploying more than one microservice at a time. You're always deploying a single microservice, a single instance, and testing the effect of the system. Now, maybe an instance of a microservice is something like an auto-scaling group, but you have to have a well-defined, bounded system that you deploy in individual steps, and then you measure, has something broken? It also means that you can use this idea to take your informal business requirements specification and turn that into invariance. Because business rules in a microservice context are often expressed in terms of message flows. I check out from a shopping cart. I need to generate an invoice. I need to send a confirmation email. I need to generate an audit trail. These things, which are, as I've just said them, informally, written in a business requirements document, often translate directly into message flows. And those message flows are things that you can then specify as invariants and then measure. And now you're, instead of testing 300 different random flows, you're testing the most important parts of the system that the people who've written the business requirements actually care about. And this gives you an awful lot of power. It gives you the ability to move quickly, and it gives you the ability to manage risk. Another important thing that this approach does is it gives you the ability to anticipate problems that you don't know are going to happen. So in the offshore oil industry, they have a particular rule around safety. So they have the usual rules, which is, you are flying a helicopter out to an oil platform to pick up people. And the pilot can only have flown for so many hours, otherwise they're grounded. And the wind speed must be below a certain amount, otherwise it's unsafe. And the helicopter must have been serviced within the last X number of weeks. But there are scenarios where all of those measures are subcritical. Right? The pilot is only allowed to fly for 10 hours and has flown for 9. The amount of fuel is only just enough. And the helicopter is due to be serviced next week. On the surface, all the measures are okay. All the invariants are met. But when you combine them together, the probability of failure is actually a lot higher, because it doesn't take very much to tip something over. So you can also combine invariants, even though all of the measures are safe, to get yet another measure of risk in the system, to see, is something subcritical going to happen, even though it looks like everything is safe. So to sum up, microservice systems, it's not sufficient to use the standard best practices that we've developed to date. Things like build servers and unit testing and our software development methodologies. You also need to measure the systems in production. And then the question becomes, what do you measure? And the most useful thing to measure is the message flow rates, not the behavior of individual services. And because you have so many flow rates, the way that you narrow that down is to ask, how do you map my business requirements into invariants expressed essentially as ratios of message flow rates? And this gives you extremely useful, directly relevant, business relevant measures of the health of the system. So if you'd like to see more about this type of stuff in practice, SenecaJS.org is the microservices framework that we use for most of our clients, and applies a lot of these principles. One of the other things that we're doing is 3 Nearform people are actually writing books on microservices. And if you follow the Nearform blog or Nearform Twitter, you'll hear more about that later this year. Those books will discuss these techniques and some of the other things that we've learned. And that is me finished. Thank you very much.